What if I told you that the fastest thing in the universe isn't actually fast at all? Welcome back to the Lazy Cosmos, where we explore the mind-bending mysteries of our universe without leaving the comfort of your couch. Today, we're tackling one of physics' most fundamental questions: why nothing can travel faster than light. In fact, what we call the speed of light is really the universe's ultimate speed limit, a cosmic law so fundamental that breaking it would literally tear reality apart. I'm about to show you why nothing, and I mean absolutely nothing, can travel faster than 299,792,458 meters per second. And trust me, the reason will completely change how you see the universe. By the end of this video, you'll understand why Einstein's speed limit isn't just a suggestion. It's the fundamental rule that holds our entire reality together. So grab your favorite drink, get comfortable, and let's dive into the cosmic speed limit that governs everything from the light hitting your eyes right now to the GPS on your phone. Let's start with the number that rules our universe: 299,792,458 meters per second. Now, I know what you're thinking. That's a pretty specific number, right? It's not a nice round 300,000 kilometers per second, like you might see in textbooks. No, this is the exact speed at which light travels through a vacuum, measured down to the very last meter per second. And here's the thing that'll blow your mind right from the start. This number is so important that it's not just measured anymore. It's actually defined. The meter itself is now defined as the distance light travels in 1/299,792,458th of a second. We've literally built our measurement of space around this cosmic speed limit. But what does this mind-boggling speed actually mean in terms we can wrap our heads around? Well, imagine you could somehow travel at the speed of light. You could circle Earth's entire equator. That's about 40,075 kilometers, 7.5 times in just 1 second. Think about that for a moment. In the time it takes you to say one Mississippi, light has wrapped around our entire planet more than 7 times. If you were standing at the North Pole and could somehow see light racing around the equator, it would look like a constant ring of light because it's moving so fast that your eyes couldn't track its individual journey around the planet. Let's put this in perspective with some cosmic distances. The Moon, our closest celestial neighbor, sits about 384,400 kilometers away from Earth on average. Light from the Moon takes about 1.3 seconds to reach your eyes. So when you look up at the Moon tonight, you're seeing it as it was 1.3 seconds ago. That might not seem like much, but it's a profound concept. You never see the Moon as it is right now. You always see it in the past, even if it's just by a tiny fraction of time. The Sun, that massive ball of nuclear fusion that powers all life on Earth, is about 150 million kilometers away. Light from the Sun takes approximately 8 minutes and 20 seconds to reach us. So when you step outside and feel the warmth of sunlight on your face, you're feeling energy that left the Sun's surface over 8 minutes ago. Now here's where it gets really wild. The nearest star to our solar system, Proxima Centauri, is about 4.24 light-years away. That means the light from that star takes 4.24 years to reach us. When astronomers look at Proxima Centauri through their telescopes, they're seeing it as it was over 4 years ago. If that star exploded tomorrow, We wouldn't know about it until 2029, and Proxima Centauri is practically next door in cosmic terms. The Andromeda Galaxy, our nearest major galactic neighbor, is about 2.5 million light-years away. The light we see from Andromeda tonight left that galaxy when our earliest human ancestors were just beginning to walk upright on the African savanna. But let's bring this back down to Earth for a moment and talk about how we even discovered that light has a finite speed. For most of human history, people assumed light traveled instantaneously. It made sense. Flip a switch, and the room lights up immediately. No delay, no waiting, just instant illumination. Even brilliant scientists like Galileo struggled with this concept. In the early 1600s, Galileo actually tried to measure the speed of light using lanterns on hilltops. He and an assistant would stand on different hills with covered lanterns. Galileo would uncover his lantern, and when his assistant saw the light, the assistant would uncover his own lantern. Galileo tried to measure the time delay, but the distance was way too small, and human reaction time was way too slow to detect light's finite speed. The first real evidence that light has a finite speed came from an unexpected source: astronomy. In 1676, a Danish astronomer named Ole Rømer was studying the moons of Jupiter, particularly Io, Jupiter's innermost large moon. Io orbits Jupiter every 42.5 hours like clockwork, disappearing behind Jupiter in a perfectly predictable eclipse cycle. But Rømer noticed something strange. When Earth was moving away from Jupiter in its orbit, Io's eclipses seemed to happen a few minutes later than predicted. When Earth was moving toward Jupiter, the eclipses happened a few minutes earlier than expected. Rømer realized what was happening. The light carrying the image of Io's eclipse had to travel different distances to reach Earth, depending on where Earth was in its orbit. When Earth was farther from Jupiter, the light had to travel a greater distance, creating a delay. When Earth was closer, the light had less distance to travel, so the eclipse appeared to happen earlier. By carefully measuring these timing differences and knowing the distances involved, Rømer calculated that light travels at about 220,000 kilometers per second. Not bad for 1676. He was actually pretty close to the real value, considering the limited precision of his instruments and the fact that the exact distances in our solar system weren't well known at the time. Over the next few centuries, scientists got better and better at measuring light speed. In 1849, French physicist Hippolyte Fizeau used an ingenious rotating gear wheel experiment. He shined light through the gaps between gear teeth, bounced it off a mirror several kilometers away, and measured how fast the wheel had to rotate for the returning light to pass back through the gaps. His measurement came out to about 315,000 kilometers per second, much closer to our modern value. Then came Albert Michelson, an American physicist, who became obsessed with measuring light speed with unprecedented precision. In the 1880s and 1920s, he conducted a series of increasingly sophisticated experiments. His most famous involved bouncing light between mirrors on mountaintops in California, using precisely machined rotating mirrors to measure the time it took light to make the journey. Michelson's final measurement, published in 1926, was 299,796 kilometers per second, incredibly close to our modern value and accurate to within about 4 kilometers per second. But here's what's really fascinating about all these measurements. They kept getting the same basic answer, regardless of the method used or the conditions under which the experiments were performed. Whether scientists measured light traveling through air in different directions relative to Earth's motion through space, or at different times of year, they always got essentially the same speed. This consistency was puzzling and would eventually lead to one of the most revolutionary discoveries in physics. Now, you might be wondering why light travels at this specific speed and not faster or slower. That's actually the wrong question to ask, and here's why. Light doesn't really choose its speed. Light travels at the speed it does, because that's the fundamental speed at which information and causality can propagate through the fabric of spacetime itself. Light just happens to be massless, so it has no choice but to travel at this maximum possible speed through the universe. Think of it this way. Imagine spacetime as a medium, kind of like water or air, but much more fundamental. Just as sound waves can only travel so fast through air because of the physical properties of air molecules, information and energy can only propagate so fast through spacetime because of the fundamental structure of spacetime itself. This maximum speed, what we call the speed of light, is really the speed of causality. It's the speed at which cause and effect can propagate through the universe. This is why the speed of light is the same for all electromagnetic radiation, not just visible light. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays all travel at exactly the same speed through a vacuum. They're all different forms of electromagnetic radiation, and they all travel at the speed of light, causality, the speed of spacetime itself. But here's something that might surprise you. Light doesn't always travel at the speed of light. I know that sounds contradictory, but hear me out. The speed we've been talking about, 299,792,458 meters per second, is the speed of light in a perfect vacuum, where there are no atoms or particles to interact with the light. When light travels through transparent materials like glass, water, or air, it slows down. In water, light travels at about 225,000 kilometers per second. In glass, it can slow down to around 200,000 kilometers per second, depending on the type of glass. This slowdown happens because light photons interact with the atoms in the material. The photons get absorbed and re-emitted by atoms, creating tiny delays that add up to a measurable reduction in speed. The ratio of light speed in vacuum to light speed in a material is called the refractive index, and it's why lenses can bend light and why objects look distorted when viewed through water. Now, here's something really mind-bending. In some exotic materials created in laboratories, scientists have managed to slow light down to just a few meters per second, slower than a bicycle. In 1999, physicist Line Howe and her team at Harvard actually slowed light down to just 17 meters per second by passing it through an ultra-cold cloud of sodium atoms. They've even managed to stop light completely and then release it again. But even in these extreme cases, the fundamental speed limit of the universe, the speed of causality, remains unchanged at 299,792,458 meters per second. This brings us to one of the most important points about the speed of light. It's not really about light at all. The speed of light is really the speed of massless particles, the speed of electromagnetic fields, the speed of gravitational waves, and ultimately, the speed at which information can travel through spacetime. Light just happens to be the most familiar example of something that travels at this cosmic speed limit. When Einstein developed his theory of special relativity in 1905, he didn't start by thinking about light specifically. He started by thinking about the laws of physics and how they should be the same for all observers moving at constant velocities relative to each other. The fact that light speed came out to be constant for all observers was a consequence of this deeper principle, not the starting point. The speed of light emerged as this fundamental constant of nature that represents the maximum speed at which any cause can have an effect, the maximum speed at which information can travel, and the speed at which massless particles must travel. This is why we sometimes call it c in physics equations, not because it stands for acceleratus, the Latin word for speed, though that's a nice coincidence. The c represents this fundamental constant of spacetime, this cosmic speed limit that governs how fast reality itself can change from one place to another. And here's the kicker that we'll explore in much more detail later in this video. This speed limit isn't just a suggestion or a practical limitation based on our current technology. It's built into the very fabric of space and time. It's not that we haven't figured out how to go faster than light yet. It's that going faster than light would require infinite energy and would violate the fundamental structure of causality itself. Breaking this speed limit wouldn't just be difficult or expensive. It would literally break the universe as we know it. So when we talk about the speed of light, we're really talking about the speed of reality, the speed of cause and effect, the speed at which the universe can update itself from moment to moment and from place to place. Light just happens to be our most familiar messenger, traveling at this cosmic speed limit, carrying information from distant stars and galaxies across the vast emptiness of space to our telescopes and our eyes, showing us the universe as it was, never as it is right now. This is why understanding the speed of light is so much more than just memorizing a big number. It's understanding one of the most fundamental properties of the universe we live in, the speed at which reality itself operates. And once you truly grasp this concept, everything else about relativity, space-time, and the strange behavior of the universe at high speeds starts to make sense. It's not just about light. It's about the very nature of existence itself. Here's where things get really mind-bending. And this is the part that most people don't fully grasp about the speed of light. Everything we've been talking about, this cosmic speed limit of 299,792,458 meters per second, isn't really about light at all. Light is just the messenger, the most familiar example of something traveling at this fundamental speed. The real star of the show is something much more profound and much more fundamental to the nature of reality itself: space-time. Now, I know the word space-time gets thrown around a lot in science videos, often without really explaining what it means or why it matters. So let's break this down from the ground up, because understanding space-time is the key to understanding why nothing can travel faster than light. Before Einstein came along in the early 1900s, we thought of space and time as two completely separate things. Space was like a big empty container where things happened, and time was like a universal clock that ticked at the same rate everywhere in the universe. You could measure distances in space with a ruler, and you could measure durations in time with a clock, and these two measurements were completely independent of each other. But Einstein realized something absolutely revolutionary. Space and time aren't separate things at all. They're two aspects of a single unified entity called spacetime. This isn't just a mathematical convenience or a fancy way of talking about physics. It's a fundamental description of the fabric of reality itself. Spacetime is the stage upon which all of physics plays out, and it has its own structure, its own properties, and most importantly, for our discussion today, its own built-in speed limit. To understand this better, let's start with something familiar. Imagine you're standing in a big, empty field, and you want to describe the location of a tree. You might say, it's 100 meters north and 50 meters east of where you're standing. You need two coordinates, north-south and east-west, to pinpoint the tree's location in the two-dimensional space of the field. Now, if you want to meet someone at that tree, you also need to specify when to meet them. You need a third coordinate, time. You might say, meet me at the tree that's 100 meters north and 50 meters east at 3 p.m. But here's where Einstein's insight becomes crucial. Just as north-south and east-west aren't really separate things, but are both directions in the same two-dimensional space, the three dimensions of space and the one dimension of time aren't really separate either. They're all directions in a single, four-dimensional space-time. This isn't just a mathematical abstraction. It's how the universe actually works at the most fundamental level. This four-dimensional space-time has a very specific structure, and that structure determines the maximum speed at which anything can move through it. Think of it this way. Imagine you're walking across that field toward the tree. You can walk north, you can walk east, or you can walk in some combination of north and east. But there's a maximum speed at which you can walk. Let's say 5 kilometers per hour. You might walk 5 kilometers per hour directly north, or 5 kilometers per hour directly east, or some combination where your total speed is still 5 kilometers per hour. You can't walk 3 kilometers per hour north and 4 kilometers per hour east simultaneously, because that would give you a total speed of 5 kilometers per hour, which is your maximum. Space-time works similarly, but with a crucial difference. In space-time, everything, and I mean everything, is always moving at exactly the same total speed through the four dimensions combined. That speed is the speed of light, 299,792,458 meters per second. You can't choose to go slower than this total speed, and you can't choose to go faster. You're always moving at exactly light speed through space-time. Now, this might sound impossible. You're probably thinking, but I'm sitting still right now. I'm not moving at the speed of light. But here's the thing. You're not moving through the three dimensions of space right now, but you are moving through the dimension of time. Every second that passes, you move 1 second into the future. You're traveling through time at a rate of 1 second per second, and that motion through time is part of your total motion through space-time. When you're sitting still in space, all of your motion through space-time is in the time direction. But when you start moving through space, when you get up and walk around, or drive in a car, or fly in an airplane, some of your motion through space-time gets redirected from the time direction into the spatial directions. The faster you move through space, the slower you move through time. This is time dilation, and it's a direct consequence of the structure of space-time itself. This is why time slows down for objects moving at high speeds. It's not some mysterious effect that happens to clocks or biological processes. It's the fundamental geometry of space-time. When you're moving very fast through space, you're using up more of your total motion through space-time in the spatial directions, which leaves less motion available for the time direction. Time literally passes more slowly for you. And here's the kicker. Light travels at the maximum possible speed through the spatial dimensions of space-time. Photons are moving so fast through space that they use up all of their motion through space-time in the spatial directions. They have no motion left over for the time direction. This is why photons don't experience the passage of time at all. From a photon's perspective, if photons could have perspectives, no time passes during their journey from a distant star to your eye, even if that journey takes millions of years from our perspective. This brings us to the fundamental speed limit of the universe. The speed of light isn't really the speed of light. It's the speed of space-time itself. It's the maximum rate at which cause and effect can propagate through the fabric of reality. This speed is built into the very structure of space-time, just like the fact that the shortest distance between 2 points is a straight line is built into the structure of ordinary space. Let me give you an analogy that might help clarify this concept. Imagine space-time as a vast highway system. Not just any highway, but a very special kind of highway with very specific rules. On this cosmic highway, there's an absolute speed limit, and that limit is 299,792,458 meters per second. But unlike speed limits on regular highways, this isn't just a legal restriction that you could theoretically break if you were willing to pay the fine. This is a physical impossibility built into the structure of the highway itself. It's as if the highway has some kind of fundamental property that makes it impossible for anything to travel faster than this speed. You could build the most powerful engine imaginable. You could have access to all the energy in the universe, but you still couldn't exceed the speed limit because the highway itself, space-time itself, simply doesn't allow it. The speed limit isn't imposed from outside. It's an intrinsic property of space-time. Now you might wonder why this speed limit exists at all. Why 299,792,458 meters per second and not some other speed? Why not twice as fast, or 10 times faster, or infinitely fast? This is one of those deep questions about the nature of reality that gets to the heart of why our universe is the way it is. The speed of light is what physicists call a fundamental constant of nature, like the electric charge of an electron or the mass of a proton. These aren't values that were chosen by some cosmic designer. They're simply the way our universe happens to be built. Different values for these fundamental constants would result in a completely different kind of universe, if such a universe could exist at all. If the speed of light were much slower, chemical reactions might not work properly, stars might not be able to shine, and complex structures like planets and life might never form. If the speed of light were much faster, or if there were no speed limit at all, the concept of causality, the idea that causes precede their effects, might break down entirely. The speed of light as the cosmic speed limit is intimately connected to the structure of causality itself. Causality is the principle that events have causes, and that these causes must occur before their effects. If you drop a glass, the cause, releasing the glass, happens before the effect, the glass hitting the floor. This seems obvious, but it's actually a deep principle that governs how reality works. The speed of light determines how fast information about a cause can travel to create its effect. When you flip a light switch, information about that action travels through the electrical circuit at close to the speed of light to reach the bulb and turn it on. When gravitational waves ripple through space-time after two black holes collide, that information travels at exactly the speed of light to eventually reach detectors here on Earth. The speed of light is the speed at which the universe can update itself. The speed at which changes in one location can influence what happens in another location. This is why we sometimes call the speed of light the speed of causality, or the speed of information. It's not just that light happens to travel at this speed. It's that this speed represents the fundamental rate at which cause and effect can propagate through spacetime. Light travels at this speed because light is massless and therefore has no choice but to travel at the maximum speed that spacetime allows. But light isn't the only thing that travels at this speed. Gravitational waves, ripples in spacetime itself caused by accelerating masses, also travel at exactly the speed of light. This isn't a coincidence. Both light and gravitational waves are traveling at the speed of spacetime, the speed at which information can propagate through the fabric of reality. Any massless particle must travel at this speed. Besides photons, particles of light, this includes gluons, which carry the strong nuclear force. Though gluons are always confined within atomic nuclei, so we don't see them traveling freely through space. If the hypothetical graviton, the particle that would carry gravitational force in a quantum theory of gravity, exists, it would also be massless and would travel at the speed of light. Massive particles, on the other hand, can never reach the speed of light. As a massive object approaches light speed, its energy increases without bound, and it would take infinite energy to actually reach light speed. This isn't a technological limitation. It's a fundamental feature of how spacetime works. Massive particles simply cannot use up all of their motion through spacetime in the spatial directions, because they always retain some motion in the time direction. This brings us to one of the most profound insights about the nature of spacetime. It's not empty. Space isn't just a void waiting to be filled with matter and energy. Spacetime itself has structure, properties, and dynamics. It can be curved by the presence of matter and energy, as Einstein showed in his general theory of relativity. It can ripple and wave, as we've detected with gravitational wave detectors. It has a maximum rate at which information can flow through it, which we call the speed of light. In a sense, spacetime is more like a material medium than an empty void, but it's a very special kind of medium. It's a medium that makes up the very fabric of reality itself. Just as the properties of water determine how fast sound waves can travel through it, the properties of spacetime determine how fast information and causality can travel through the universe. This is why the speed of light is so much more than just a speed. It's a window into the fundamental structure of reality itself. It tells us about the nature of space and time, about how cause and effect work, about the maximum rate at which the universe can change from moment to moment to moment and from place to place. When we measure the speed of light, we're not just measuring how fast photons move. We're probing the fundamental geometry of space-time, the arena in which all of physics plays out. We're discovering the cosmic speed limit that governs everything from the smallest quantum interactions to the largest scale structure of the universe. Understanding spacetime and its built-in speed limit is crucial for understanding why nothing can travel faster than light. It's not that we haven't figured out how to build faster spaceships or more powerful engines. It's that the very fabric of reality has a maximum speed built into it, and exceeding that speed would require fundamentally changing the nature of spacetime itself. This cosmic speed limit shapes everything about how our universe works. It determines how quickly information can travel, how fast changes can propagate, how rapidly cause and effect can unfold across the cosmos. It's the heartbeat of reality itself, the fundamental rhythm that governs how the universe evolves from moment to moment. Without this speed limit, the universe would be a very different place. Causality might not work the way it does. The relationship between space and time might be completely different. The very concept of now might not make sense across different locations in space. The speed of light isn't just a property of light. It's a fundamental feature of the cosmos that makes our universe the orderly, comprehensible place it is. So when we talk about why nothing can travel faster than light, we're really talking about why nothing can travel faster than the speed at which space-time itself allows information and causality to propagate. We're talking about a speed limit that's woven into the very fabric of reality, as fundamental and unchangeable as the fact that triangles have three sides, or that circles are round. This is the true significance of the speed of light. It's not just about light, and it's not just about speed. It's about the deepest, most fundamental properties of the universe we live in, the structure of space-time itself, and the cosmic speed limit that governs how fast reality can change. In 1905, a young patent clerk in Bern, Switzerland, was about to turn our understanding of reality completely upside down. Albert Einstein wasn't working at a prestigious university. He wasn't surrounded by the latest scientific equipment, and he wasn't even primarily focused on physics during his day job. He was examining patent applications for electromagnetic devices, making sure inventors' claims were scientifically sound. But in his spare time, this 26-year-old was wrestling with some of the deepest questions about the nature of light, space, and time that had been puzzling physicists for decades. The problem that kept Einstein awake at night was something that had been bothering scientists since the late 1800s. They had discovered that light behaves like a wave. It can interfere with itself. It can be diffracted around obstacles, and it exhibits all the properties we expect from waves. But here's the thing about waves. They need something to wave in. Sound waves travel through air. Water waves travel through water. Earthquake waves travel through solid rock. So what did light waves travel through as they journeyed from the sun to Earth through the seemingly empty vacuum of space? Scientists at the time proposed that space must be filled with an invisible, undetectable substance they called the luminiferous ether. Literally, the light-bearing ether. This ether was supposed to be the medium through which light waves propagated, just like air is the medium through which sound waves propagate. The ether had to have some very strange properties to work as proposed. It had to be rigid enough to support the incredibly high-frequency vibrations of light waves, yet it had to be so tenuous that planets could orbit through it without any resistance. It had to fill all of space, yet be completely undetectable by any direct means. The existence of this ether led to a testable prediction. If Earth was moving through the ether as it orbited the Sun, then the speed of light should appear different depending on whether you measured it in the direction of Earth's motion through the ether or perpendicular to that motion. It's like the difference between swimming with the current versus swimming across the current in a river. The water's motion affects your effective speed relative to the riverbank. In 1887, two American physicists, Albert Michelson and Edward Morley, designed an incredibly sensitive experiment to detect Earth's motion through the ether. They used an ingenious device called an interferometer that could split a beam of light, send the two halves in perpendicular directions, reflect them back with mirrors, and then recombine them to look for tiny differences in the time it took each beam to complete its journey. If Earth was moving through the ether, one beam should take slightly longer than the other, and this difference would show up as a shift in the interference pattern when the beams were recombined. The Michelson-Morley experiment was a masterpiece of precision measurement, and it gave a completely unexpected result. No difference at all. No matter which direction they pointed their interferometer, no matter what time of year they performed the experiment, no matter how they oriented their apparatus, they always got the same answer. The speed of light appeared to be exactly the same in all directions. It was as if Earth wasn't moving through the ether at all, which made no sense because Earth is clearly moving in its orbit around the Sun. This null result created what physicists call a crisis. Either the ether didn't exist, which seemed impossible because then what did light waves propagate through? Or Earth wasn't moving through the ether, which seemed equally impossible because we know Earth orbits the Sun. Some physicists proposed that maybe Earth somehow dragged the ether along with it, but that led to other contradictions. Others suggested that maybe objects contracted in the direction of their motion through the ether by just the right amount to hide the effect, but this seemed like an ad hoc fix rather than a fundamental explanation. This is where Einstein came in with his revolutionary insight. Instead of trying to explain away the null result of the Michelson-Morley experiment, Einstein took it seriously as a fundamental clue about the nature of reality. He started with two simple postulates that flew in the face of common sense, but were consistent with all the experimental evidence. First, the laws of physics are the same in all inertial reference frames. This means that if you're moving at constant velocity, whether you're sitting still, cruising in a car, or flying in an airplane, the laws of physics work exactly the same way for you. There's no experiment you can do inside your reference frame to determine whether you're moving or stationary. This principle, called the principle of relativity, actually dates back to Galileo, but Einstein extended it to include electromagnetic phenomena like light. Second, and this is the revolutionary part, the speed of light in a vacuum is the same for all observers, regardless of their motion. This sounds impossible, but it's exactly what the Michelson-Morley experiment had shown. Whether you're moving toward a source of light or away from it, whether you're stationary or traveling at high speed, you always measure the same value for the speed of light, 299,792,458 meters per second. Now, let's think about why this second postulate is so mind-bending. In our everyday experience, velocities add and subtract in intuitive ways. If you're in a car traveling at 60 kilometers per hour and you throw a ball forward at 20 kilometers per hour, relative to the car, someone standing on the roadside sees the ball moving at 80 kilometers per hour. If you throw the ball backward at 20 kilometers per hour, relative to the car, the roadside observer sees it moving at 40 kilometers per hour. This is basic addition and subtraction of velocities, and it works perfectly for everyday objects. But Einstein was saying that light doesn't work this way at all. If you're in a spaceship traveling at half the speed of light and you shine a flashlight forward, you don't see the light traveling away from you at half the speed of light, and an outside observer doesn't see the light traveling at 1.5 times the speed of light. Both you and the outside observer measure exactly the same speed for the light, the standard speed of light. This seems to violate basic arithmetic, but it's exactly what experiments show. The only way this can work is if space and time themselves are flexible, adjusting themselves to ensure that everyone always measures the same speed for light. This was Einstein's great insight. Space and time are not the fixed, absolute backdrop that Newton had assumed. They're dynamic, relative quantities that depend on the motion of the observer. This leads to the famous effects of special relativity, starting with time dilation. If space and time must adjust to keep the speed of light constant for all observers, then time itself must run at different rates for observers, moving at different velocities relative to each other. Specifically, time runs slower for objects moving at high speeds relative to you. This isn't just an effect on clocks or biological processes. Time itself literally passes more slowly. The mathematical relationship is given by what's called the Lorentz factor, named after Dutch physicist Hendrik Lorentz, who derived it before Einstein, but didn't fully understand its physical meaning. The Lorentz factor is 1 divided by the square root of 1 minus v squared over c squared, where v is the velocity of the moving object and c is the speed of light. When v is much smaller than c, which is the case for all everyday speeds, this factor is very close to 1, meaning time dilation is negligible. But as v approaches c, the Lorentz factor approaches infinity, meaning time dilation becomes extreme. Let's put some numbers to this. If you're traveling at 10% the speed of light, time runs about 0.5% slower for you compared to someone at rest. That's a tiny effect, but it's measurable with precise clocks. At 50% the speed of light, time runs about 13% slower. At 90% the speed of light, time runs more than twice as slowly. What feels like 1 hour to you would be more than 2 hours for someone at rest. At 99% the speed of light, time runs about 7 times more slowly. And as you approach 100% the speed of light, time dilation approaches infinity. Time would essentially stop for you relative to the outside world. This isn't science fiction. It's measurable, observable reality. Particles and cosmic rays routinely travel at speeds very close to the speed of light, and we can observe their time dilation directly. Muons, which are unstable particles that normally decay in about 2 microseconds, can travel much farther through Earth's atmosphere than they should be able to, because time dilation extends their lifetimes from our perspective. GPS satellites, which orbit Earth at high speeds, experience measurable time dilation that must be corrected for the system to work accurately. But time dilation is just the beginning. Einstein's special relativity also predicts length contraction. Objects become shorter in the direction of their motion as they approach the speed of light. From the perspective of a stationary observer, a rapidly moving object appears to contract by the same Lorentz factor that governs time dilation. At 90% the speed of light, an object appears to be compressed to less than half its original length. At 99% the speed of light, it appears to be compressed to about 1/7 its original length. Crucially, this contraction only occurs in the direction of motion. A sphere moving at high speed would appear flattened into an ellipsoid from the perspective of a stationary observer, but it would appear perfectly spherical to someone moving along with it. Like time dilation, length contraction is a real physical effect, not just an optical illusion. These effects, time dilation and length contraction, are the universe's way of ensuring that the speed of light remains constant for all observers. As objects approach the speed of light, time slows down and lengths contract in just the right way to keep the ratio of distance to time, which is speed, equal to c for any light beam, regardless of the motion of the observer. But perhaps the most famous consequence of Einstein's special relativity is the equivalence of mass and energy, expressed in the equation E equals mc squared. This equation tells us that mass and energy are really two forms of the same thing. A small amount of mass can be converted into an enormous amount of energy, and energy can be converted into mass. The factor of conversion is c squared, the speed of light squared, which is an incredibly large number. This mass-energy equivalence has profound implications for our question about why nothing can travel faster than light. As an object with mass accelerates, its kinetic energy increases. But according to E equals mc squared, this additional energy contributes to the object's effective mass, making it harder to accelerate further. The faster an object goes, the more energy is required to make it go even faster. As the object's speed approaches the speed of light, its effective mass approaches infinity, and therefore the energy required to accelerate it further also approaches infinity. This creates an insurmountable barrier. To accelerate any massive object to exactly the speed of light would require infinite energy, which is impossible. The universe simply doesn't contain infinite energy. Even if it did, adding infinite energy to an object would give it infinite mass, which would create other impossible conditions like infinite gravitational attraction. This is why massive objects can approach the speed of light but can never quite reach it. In particle accelerators, like the Large Hadron Collider, we can accelerate protons to 99.9999991% of the speed of light. But that last tiny fraction of a percent requires enormous amounts of additional energy. Each incremental increase in speed near the speed of light requires exponentially more energy. Only massless particles can travel at the speed of light, and they have no choice in the matter. Photons, which have no mass, must travel at exactly the speed of light. They can't go slower, and they can't go faster. From their perspective, if they could have a perspective, no time passes during their journey across the universe. The photons that left the sun 8 minutes ago and are hitting your eyes right now experience no time during their journey from the sun's surface to your retina. Einstein's special relativity also reveals another profound truth about the nature of simultaneity. Events that appear to happen at the same time for one observer may not be simultaneous for another observer moving at a different velocity. This relativity of simultaneity means that there's no universal now that applies throughout the universe. The concept of simultaneity is relative depending on the motion of the observer. This has mind-bending implications. Imagine two events happening on opposite sides of the galaxy. One observer might see event A happen before event B, while another observer, moving at high speed relative to the first, might see event B happen before event A. As long as the events are far enough apart in space and close enough together in time that light couldn't travel from one to the other, both observations are equally valid. There's no objective truth about which event really happened first. This relativity of simultaneity is intimately connected to the cosmic speed limit. The speed of light defines not just the maximum speed at which objects can travel, but also the maximum speed at which information and causality can propagate. Events can only influence each other if they're close enough in space and separated enough in time for a light signal to travel from one to the other. This defines what physicists call the light cone, the region of spacetime that can be causally connected to any given event. The genius of Einstein's special relativity is that it takes the strange, seemingly impossible result of the Michelson-Morley experiment and reveals it to be a fundamental feature of the universe. The constancy of the speed of light isn't a puzzling anomaly to be explained away. It's a deep truth about the nature of space-time that reveals the flexible, relative nature of space and time themselves. Before Einstein, we thought space and time were fixed, absolute backgrounds against which physics played out. After Einstein, we understood that space and time are dynamic participants in physical processes, stretching and contracting, to maintain the cosmic speed limit that governs the propagation of information and causality throughout the universe. This transformation in our understanding of space, time, and the speed of light set the stage for even more revolutionary discoveries. Einstein's special relativity, published in 1905, was just the beginning. 10 years later, he would extend these ideas to include gravity and acceleration in his general theory of relativity, revealing that massive objects actually curve spacetime itself, and that this curvature is what we experience as gravitational attraction. But even special relativity alone was enough to completely revolutionize physics and our understanding of the universe. It showed us that the speed of light isn't just a property of light. It's a fundamental feature of spacetime that determines how fast reality itself can change from place to place and moment to moment. It revealed that space and time are not separate, absolute entities, but aspects of a unified spacetime that has its own intrinsic structure and limitations. Most importantly, for our discussion today, Einstein's special relativity showed us exactly why nothing can travel faster than light. It's not a technological limitation or a practical constraint. It's a fundamental feature of the universe itself, built into the very fabric of spacetime. The speed of light is the speed of causality, the speed of information, the speed at which the universe can update itself from moment to moment. And that speed limit is absolute, unchangeable, and inviolable, not because we haven't figured out how to break it, but because breaking it would require fundamentally changing the nature of reality itself. Now that we understand how Einstein's special relativity revealed the flexible nature of space and time, let's dive deep into the actual physics that creates this seemingly impenetrable barrier at the speed of light. This is where we move from the conceptual understanding of why the speed limit exists to the mathematical reality of what happens when you try to approach it. The physics behind this barrier is both elegant and absolutely unforgiving. It's not just difficult to reach the speed of light, it's literally impossible for anything with mass. Let's start with the most fundamental equation that governs this barrier, the relativistic energy equation. In Einstein's special relativity, the total energy of an object is given by E equals mc squared divided by the square root of 1 minus v squared over c squared, where m is the object's rest mass, v is its velocity, and c is the speed of light. This equation might look intimidating, but it contains within it the complete explanation for why nothing with mass can reach light speed. The denominator of this equation, the square root of 1 minus v squared over c squared, is our old friend the Lorentz factor, but this time it's in the denominator, which makes all the difference. When an object is at rest, v equals 0, so the denominator equals 1, and the total energy is just mc squared, Einstein's famous mass-energy equivalence. But as the object's velocity increases, v squared over c squared gets larger, making the denominator smaller, which makes the total energy larger. Here's where things get really interesting mathematically. As v approaches c, the term v squared over c squared approaches 1. This means the denominator approaches 0. And when you divide any non-zero number by something approaching 0, the result approaches infinity. So as an object with mass approaches the speed of light, its total energy approaches infinity. This isn't just a large number, it's literally infinite, meaning no amount of energy in the universe would be sufficient to accelerate a massive object to exactly light speed. Let's put some concrete numbers to this to see how brutal this energy barrier becomes. Imagine we have a small object with a mass of just 1 kilogram, about the mass of a textbook. If this object is moving at 50% the speed of light, its total energy is about 1.15 times mc squared, meaning it has about 15% more energy than when it was at rest. That's a significant increase, but still manageable. At 90% the speed of light, the energy increases to about 2.29 times mc squared, more than double the rest energy. At 99% the speed of light, we're looking at about 7.09 times mc squared. At 99.9% the speed of light, the energy is about 22.4 times mc squared. Notice how the energy requirements are growing exponentially as we approach light speed. At 99.99% the speed of light, our 1 kilogram object would have a total energy of about 70.7 times mc squared. At 99.999%, it's about 223.6 times mc squared. At 99.9999%, it's about 707.1 times mc squared. Each additional 9 in the percentage requires roughly triple the energy of the previous step. The energy requirements don't just increase, they explode exponentially as you get closer to light speed. To put this in perspective, let's consider what these energies actually mean. The rest energy of a 1 kilogram object is mc squared, which equals about 9 times 10 to the 16th power joules. That's about 25 billion kilowatt hours, roughly the amount of energy a large city uses in a month. At 99.9999% the speed of light, our 1 kilogram object would need about 707 times this amount of energy, roughly equivalent to all the energy used by human civilization in several centuries, just to accelerate a single kilogram of matter to within 0.0001% of light speed. And we're still not at light speed. To actually reach 100% of light speed would require infinite energy, which is clearly impossible. There isn't infinite energy available in the universe, and even if there were, adding infinite energy to an object would create other impossibilities, like infinite gravitational attraction that would collapse the entire universe into a singularity. This energy barrier manifests itself in particle accelerators, where we routinely push particles to speeds very close to light speed. The Large Hadron Collider, the most powerful particle accelerator ever built, can accelerate protons to 99.9999991% of the speed of light. Each proton in the LHC has an energy of about 6.5 trillion electron volts, which is about 7,000 times the proton's rest energy. To reach this incredible speed, the LHC requires superconducting magnets cooled to temperatures colder than outer space and consumes about 1.3 terawatt hours of electricity per year, enough to power a large city. But even with all this incredible technology and energy expenditure, the LHC can't reach exactly light speed. That last 0.0000009% of light speed would require exponentially more energy than is practically available on Earth, and eventually more energy than exists in the observable universe. The reason for this energy barrier lies in the fundamental relationship between energy, momentum, and mass in special relativity. In classical physics, kinetic energy increases as the square of velocity. KEE equals half mv squared. This means doubling the speed quadruples the kinetic energy. But in relativistic physics, the relationship is much more complex and much more severe. In relativity, momentum is defined as P equals mv divided by the square root of 1 minus v squared over c squared. Just like energy, momentum also approaches infinity as velocity approaches light speed. This creates what physicists call the relativistic mass effect, though modern physicists prefer to think of it as an increase in the object's resistance to further acceleration rather than an actual increase in mass. As an object approaches light speed, it becomes harder and harder to accelerate it further. It's not just that you need more force to get the same acceleration. You need exponentially more force for smaller and smaller gains in speed. The object acts as if it's becoming more and more massive, requiring more and more energy to achieve smaller and smaller increases in velocity. This leads us to another way of understanding the light speed barrier, the concept of form momentum in spacetime. Just as objects have three-dimensional momentum in space, they also have four-dimensional momentum in spacetime. The magnitude of this form momentum is always equal to mc for any object with rest mass m, regardless of how fast the object is moving. In spacetime, an object's form momentum can be divided between its momentum through the three spatial dimensions and its momentum through the time dimension. When an object is at rest in space, all of its form momentum is in the time direction. As the object accelerates through space, some of its form momentum gets redirected from the time direction to the spatial directions. The key insight is that the total magnitude of form momentum is conserved and equal to mc. As more and more form momentum gets redirected to spatial motion, less and less remains for temporal motion, which is why time dilation occurs. But there's a fundamental limit. All of the form momentum can be redirected to spatial motion only if m equals 0. That is, only for massless particles. For any object with non-zero rest mass, some form momentum must always remain in the time direction. This means the object can never quite reach light speed, no matter how much energy you add to it. The energy goes into increasing the magnitude of the spatial component of form momentum. But since the total form momentum magnitude is fixed at mc, the object can approach but never reach the point where all form momentum is spatial. This brings us to the quantum mechanical perspective on the light speed barrier. In quantum field theory, particles are excitations of underlying quantum fields that permeate all of spacetime. Massive particles correspond to excitations of fields that have a non-zero mass parameter, while massless particles correspond to excitations of fields that have a zero mass parameter, fields with zero mass parameter. The mass parameter in quantum field theory isn't just a label. It determines the fundamental properties of the particle, including how it interacts with spacetime. Particles with non-zero mass are always associated with a rest frame, a reference frame in which the particle is at rest. Massless particles, on the other hand, have no rest frame. They exist only at light speed and can never be slowed down or brought to rest. This quantum field theory perspective reveals why the light speed barrier is so fundamental. It's not just a limitation on how fast we can push objects. It's built into the very definition of what it means to be a massive versus massless particle. Massive particles are fundamentally different types of entities from massless particles, with completely different relationships to spacetime from the perspective of thermodynamics and statistical mechanics. The light speed barrier also makes perfect sense. The second law of thermodynamics tells us that entropy, roughly speaking, the amount of disorder in a system, always increases over time. Reaching light speed would require adding infinite energy to an object, which would require infinite work, which would create infinite entropy. This would violate the second law of thermodynamics on a cosmic scale. Moreover, if massive objects could reach light speed, it would create causality paradoxes. Objects moving faster than light could, in principle, be used to send information into the past, creating logical contradictions like the grandfather paradox. The light speed barrier isn't just about energy. It's about preserving the logical consistency of cause and effect throughout the universe. The barrier also emerges naturally from the geometry of spacetime itself. In the mathematical framework of special relativity, spacetime has what's called a Minkowski metric, which defines how distances and times are measured. This metric has a built-in light cone structure that separates spacetime into regions that can be causally connected and regions that cannot. The light speed barrier corresponds to the boundary of this light cone. Events inside the light cone can influence each other because signals traveling at or below light speed can connect them. Events outside each other's light cones cannot influence each other because it would require faster-than-light signaling. The light speed barrier isn't imposed on spacetime from outside. It emerges naturally from spacetime's own geometric structure. This geometric perspective also explains why the light speed barrier is the same for all types of interactions, not just electromagnetic ones. Gravitational waves travel at light speed. The strong and weak nuclear forces are also limited by light speed, and even hypothetical new forces or particles must respect this cosmic speed limit. It's not about the specific physics of electromagnetism. It's about the fundamental geometry of spacetime itself. In particle physics experiments, we see this barrier in action every day. When high-energy cosmic rays hit Earth's atmosphere, they create showers of particles, many of which are moving at speeds very close to light speed. These particles follow exactly the predictions of special relativity. Their lifetimes are extended by time dilation. Their paths are curved by length. Contraction-contraction effects, and their energies follow the relativistic energy-momentum relationship Precisely. The most dramatic example is in the behavior of neutrinos, nearly massless particles that zip through matter at speeds incredibly close to light speed. For decades, physicists thought neutrinos were exactly massless and traveled at exactly light speed. But careful experiments revealed that neutrinos have tiny but non-zero masses, which means they travel at very slightly less than light speed. This small difference from light speed has huge implications for neutrino astronomy and cosmology. The light speed barrier also appears in the phenomenon of Cherenkov radiation. When a charged particle travels through a medium faster than light travels through that same medium, it creates a shock wave of electromagnetic radiation, the optical equivalent of a sonic boom. But even in Cherenkov radiation, the particle never exceeds the speed of light in vacuum. It only exceeds the speed of light in the specific medium, which is always less than c. Perhaps most remarkably, the light speed barrier is self-reinforcing. As objects approach light speed, relativistic effects become stronger, making it even harder to approach light speed further. Time dilation means that processes within the accelerating object slow down. Length contraction means the object becomes more compact. The increasing energy requirements mean that any acceleration mechanism becomes less and less effective. It's as if the universe has multiple backup systems, all designed to enforce the same speed limit. You can't circumvent the energy barrier by using a different type of force, because all forces are limited by the same relativistic effects. You can't circumvent it by using quantum mechanical effects, because quantum field theory respects the same space-time structure. You can't circumvent it by using exotic matter or energy, because all matter and energy must obey the same fundamental laws. This is why the light speed barrier is absolute and inviolable. It's not a technological limitation that we might someday overcome with better engineering or more advanced physics. It's woven into the very fabric of reality at the most fundamental level. Breaking the light speed barrier wouldn't just require better technology, it would require rewriting the basic laws of physics and restructuring space-time itself. The beauty of this barrier is that it's both simple and profound. Simple because it can be expressed in straightforward mathematical terms that follow inevitably from Einstein's two basic postulates about the constancy of light speed and the equivalence of inertial reference frames. Profound because it reveals deep truths about the nature of space, time, causality, and the fundamental structure of reality itself. This is the physics behind the barrier that prevents anything with mass from reaching light speed. It's not just one effect, but a convergence of multiple fundamental principles: energy conservation, the geometry of space-time, the structure of quantum fields, the requirements of causality, and the basic mathematics of four-dimensional physics. All of these different aspects of physics point to the same conclusion. The speed of light is not just fast. It's the absolute cosmic speed limit that governs how fast reality itself can change from place to place and moment to moment. Now that we've explored the fundamental physics behind the light speed barrier, let's delve into the truly mind-bending consequences that emerge from this cosmic speed limit. These aren't just abstract mathematical curiosities. They're real, measurable effects that fundamentally alter our understanding of reality and have practical applications that touch your daily life in ways you might never have imagined. The consequences of the light speed limit reveal just how strange and wonderful our universe really is when you dig beneath the surface of everyday experience. Let's start with one of the most profound and counterintuitive consequences, the relativity of simultaneity. In our everyday experience, we have a strong intuitive sense that events either happen at the same time or they don't. If two lightning bolts strike at exactly 3 p.m., we naturally assume they happen simultaneously, regardless of where we are or how fast we're moving. But Einstein's special relativity completely destroys this intuitive notion of universal simultaneity. The relativity of simultaneity tells us that whether two events are simultaneous depends entirely on the motion of the observer. Two events that appear perfectly simultaneous to one observer may happen at completely different times for another observer moving at high speed relative to the first. This isn't just a measurement error or an optical illusion. It's a fundamental feature of how spacetime works. Here's a concrete example that illustrates just how strange this gets. Imagine two space stations positioned on opposite sides of our solar system, about 10 billion kilometers apart. Now suppose that at exactly the same time, from the perspective of someone at rest relative to the solar system, both space stations send out identical radio signals. An observer at rest in the solar system would measure these signals as being sent simultaneously. But now consider an observer traveling at 90% the speed of light from one station toward the other. Due to the relativity of simultaneity, this high-speed observer would measure one signal as being sent about 19 minutes before the other signal. The events that were simultaneous for the stationary observer are separated by nearly 20 minutes for the moving observer. And here's the kicker. Both measurements are equally valid. There's no correct answer about which signal was really sent first. This has profound implications for our concept of now on a cosmic scale. The idea of a universal, present moment that applies throughout the universe simply doesn't exist. Your now is different from the now of someone moving relative to you, and both are equally valid. When you look up at the stars at night and think about what might be happening right now on distant planets, you're asking a question that has no objective answer. The concept of simultaneity only makes sense within a specific reference frame. This leads us to one of the most famous thoughts, experiments in physics, the twin paradox. This paradox perfectly illustrates how the light speed limit creates effects that challenge our deepest intuitions about time. Imagine identical twins, Alice and Bob. Alice stays on Earth, while Bob travels to a nearby star at 90% the speed of light. The journey to the star takes about 4.8 years from Earth's perspective, and the return journey takes another 4.8 years, for a total trip time of about 9.6 years. But here's where it gets weird. Due to time dilation, time passes much more slowly for Bob during his high-speed journey. At 90% light speed, time runs about 2.29 times slower for Bob than for Alice. So while Alice experiences 9.6 years passing on Earth, Bob experiences only about 4.2 years during his journey. When Bob returns to Earth, he's about 5.4 years younger than Alice, even though they started as identical twins. This isn't science fiction. It's measurable, observable physics. The effect has been confirmed with atomic clocks on airplanes, with particles in accelerators, and with observations of cosmic rays. Time dilation is real, and it means that high-speed travel is literally a form of time travel into the future. Bob has traveled about 5.4 years into Alice's future simply by moving at high speed relative to her. The twin paradox gets even stranger when you consider it from Bob's perspective during the journey. From Bob's point of view, he's at rest, and Earth is moving away from him at 90% light speed. So shouldn't Alice be the one experiencing time dilation? This apparent contradiction is resolved by the fact that Bob must accelerate and decelerate during his journey, breaking the symmetry between the two reference frames. The twin who accelerates is the one who ends up younger, but the consequences of the light speed limit go far beyond thought experiments. They show up in technologies you use every day. The Global Positioning System, GPS, provides a perfect real-world example of how relativistic effects matter for practical applications. GPS satellites orbit Earth at speeds of about 14,000 kilometers per hour, at altitudes of about 20,000 kilometers above Earth's surface. At these speeds, the satellites experience measurable time dilation. Time runs about 7 microseconds per day, slower on the satellites compared to clocks on Earth's surface. That might sound insignificant, but GPS works by measuring the time it takes radio signals to travel from satellites to receivers. Light travels about 300 meters per microsecond, so a 7 microsecond error in timing translates to about 2.1 kilometers of position error per day. But that's not all. The satellites are also higher up in Earth's gravitational field, which causes another relativistic effect from Einstein's general relativity: gravitational time dilation. Time runs faster in weaker gravitational fields, so the satellite clocks actually run about 45 microseconds per day, faster than Earth surface clocks due to this effect. Combining both effects, satellite clocks run about 38 microseconds per day, faster than Earth clocks. If GPS didn't account for these relativistic effects, the system would accumulate position errors of several kilometers per day, making it completely useless for navigation. Every time you use your phone's GPS to get directions, you're relying on Einstein's theories about the speed of light and the nature of spacetime being correct. The engineers who built GPS had to program Einstein's equations into the system for it to work at all. This brings us to another mind-bending consequence: length contraction. Just as time dilates for moving objects, lengths contract in the direction of motion. An object moving at high speed becomes shorter along its direction of travel, as measured by a stationary observer. At 90% light speed, an object appears to contract to about 44% of its original length. At 99% light speed, it contracts to about 14% of its original length. But here's what makes this truly strange. The contraction is completely reciprocal and relative. If you're moving at high speed relative to me, I see you contracted, but you see yourself as perfectly normal and see me as contracted. Both observations are equally valid. There's no absolute correct length for any object. Length is relative to the observer, just like time. Length contraction leads to some bizarre paradoxes. Consider the famous pole and barn paradox. Imagine a pole that's 10 meters long in its rest frame and a barn that's 8 meters long in its rest frame. Normally, the pole is too long to fit inside the barn. But if the pole is moving at high speed, length contraction makes it appear shorter to someone at rest with the barn. At the right speed, the contracted pole appears to be only 6 meters long and fits comfortably inside the 8-meter barn. But from the pole's perspective, it's the barn that's contracted. The pole sees itself as 10 meters long, and the barn as only about 4.8 meters long. From this perspective, the pole definitely doesn't fit in the barn. Both viewpoints are correct within their respective reference frames, but they seem to contradict each other. The resolution involves the relativity of simultaneity. The events pole fully inside barn and barn doors closed simultaneously are not simultaneous in all reference frames. These effects become even more dramatic when we consider what happens to particles moving at speeds very close to light speed. In particle accelerators and cosmic ray showers, we routinely observe particles moving at 99.99% of light speed or faster. These particles experience extreme time dilation and length contraction effects. Consider muons, created by cosmic rays in Earth's upper atmosphere. Muons are unstable particles that decay with a half-life of about 2.2 microseconds in their rest frame. At light speed, they could travel only about 660 meters before half of them decay. So muons created 50 kilometers up in the atmosphere shouldn't be able to reach Earth's surface. They should all decay long before getting here. But we detect lots of muons at Earth's surface. How is this possible? The answer is time dilation. These cosmic ray muons are moving at speeds very close to light speed, often 99.9% or faster. At these speeds, time dilation extends their lifetimes dramatically. What feels like 2.2 microseconds to the muon corresponds to much longer times from our perspective, giving them plenty of time to reach the surface. From the muon's perspective, something equally strange is happening. The muon experiences its normal 2.2 microsecond lifetime, but the atmosphere appears contracted along its direction of motion. The 50-kilometer thick atmosphere appears to be only a few hundred meters thick, allowing the muon to easily traverse it in its brief lifetime. Both explanations are correct and equivalent. Time dilation from our perspective, length contraction from the muon's perspective. This demonstrates the deep interconnectedness of space and time in Einstein's relativity. The light speed limit also creates paradoxes related to acceleration and force. In classical physics, if you apply a constant force to an object, it accelerates constantly, and its speed increases without limit. But in relativity, as an object approaches light speed, the same force produces less and less acceleration. The object becomes more and more resistant to further acceleration, as if its mass were increasing. This leads to the concept of relativistic mass, though modern physicists prefer to think of it as the object's increasing resistance to acceleration rather than an actual change in mass. A particle moving at 99% light speed acts as if it has about 7 times its rest mass when you try to accelerate it further. At 99.9% light speed, it acts as if it has about 22 times its rest mass. This effect is readily observable in particle accelerators. As particles approach light speed, it becomes exponentially more difficult to make them go faster. The most powerful accelerators in the world can push particles to within a tiny fraction of light speed, but that last tiny bit requires enormous amounts of additional energy. The light speed limit also affects how we think about causality and free will. If information cannot travel faster than light, then events happening right now on distant planets cannot immediately influence events here on Earth. Your decisions and actions can only influence events within your future light cone, the region of space-time that can be reached by signals traveling at or below light speed from your current location. This creates what physicists call the causal structure of space-time. Events can only influence other events if they're connected by time-like or light-like intervals, paths through spacetime that massive objects or light signals can actually traverse. Events separated by space-like intervals cannot influence each other because it would require faster-than-light signaling. This causal structure has deep implications for our understanding of determinism and free will. In a universe with a finite light speed, there are fundamental limits on how quickly information can propagate and how rapidly one event can influence another. The universe is not a completely interconnected whole where everything instantly affects everything else. It's a collection of causally connected regions separated by the fundamental speed limit of light. One of the most profound consequences relates to our understanding of energy and momentum conservation. In classical physics, energy and momentum are separate, conserved quantities. But in relativity, they're unified into a single four-dimensional energy-momentum vector. This unification leads to Einstein's famous E=mc2 equation and reveals the deep connection between mass and energy. This has practical consequences for nuclear physics and particle physics. In nuclear reactions, small amounts of mass are converted into large amounts of energy according to E=mc2. The enormous energy release in nuclear weapons and nuclear power plants comes from this mass energy conversion. Without relativistic effects, these processes would be impossible to understand. In particle physics, the creation and annihilation of particles routinely demonstrates mass energy conversion. When high-energy photons collide, they can create particle-antiparticle pairs, converting pure energy into mass. When particles and antiparticles annihilate, they convert their mass back into pure energy in the form of photons. These processes are only possible because of the deep connection between mass and energy revealed by the light speed limit. Perhaps most remarkably, the light speed limit affects our understanding of the universe's structure on the largest scales. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is limited by the finite speed of light and the finite age of the universe. We can only see objects whose light has had time to travel to us, creating a kind of cosmic horizon. This means there are regions of the universe that are forever beyond our ability to observe, not because they don't exist, but because light from them has not had time to reach us. The light speed limit creates fundamental boundaries on what we can know about the universe, regardless of how advanced our technology becomes. The cosmic microwave background radiation, the afterglow of the Big Bang, provides a perfect example of these light speed effects on cosmic scales. This radiation has been traveling toward us for about 13.8 billion years, since the universe became transparent to light about 380,000 years after the Big Bang. When we observe this radiation today, we're seeing the universe as it was billions of years ago, providing a direct window into the early history of the cosmos. All of these consequences, time dilation, length contraction, the relativity of simultaneity, mass energy equivalence, causal structure, and cosmic horizons, emerge from the single, simple fact that nothing can travel faster than light. The light speed limit doesn't just set a maximum velocity. It fundamentally restructures our understanding of space, time, causality, and reality itself. These effects reveal that the universe is far stranger and more wonderful than our everyday experience suggests. Space and time are not the fixed, absolute backdrop that Newton envisioned, but dynamic, relative quantities that depend on motion and gravity. Mass and energy are not separate things, but different aspects of a single underlying reality. Causality is not instantaneous, but limited by the finite speed at which information can travel. The beauty of these consequences is that they all hang together in a perfectly consistent, mathematically elegant framework. Every strange prediction of relativity has been confirmed by experiment and observation. The universe really does work this way, and the light speed limit is the key that unlocks our understanding of this deeper reality. These mind-bending consequences show us that the question, why can't anything travel faster than light, is really asking about the fundamental structure of reality itself. The answer reveals truths about space, time, causality, and existence that are far more profound and far-reaching than we might have expected from such a simple question about speed limits. Now that we've explored the seemingly impenetrable barrier that prevents anything from traveling faster than light, you're probably wondering if there are any clever ways around this cosmic speed limit. After all, human ingenuity has found workarounds for countless seemingly impossible problems throughout history. We've learned to fly despite gravity, to communicate instantly across vast distances despite physical separation, and to harness the power of the atom despite its microscopic size. So surely, there must be some loophole, some clever trick, or some exotic physics that could allow us to circumvent Einstein's speed limit, right? This is where we need to examine some of the most fascinating and often misunderstood phenomena in modern physics. Over the past several decades, scientists have discovered effects that, at first glance, seem to violate the speed of light barrier. We've observed quantum entanglement, which Einstein himself called spooky action at a distance, where particles seem to instantly affect each other across vast distances. We've developed theoretical frameworks for warp drives that could theoretically allow faster-than-light travel without violating relativity. We've explored the mathematical possibility of wormholes, shortcuts through space-time itself that could connect distant regions of the universe. But here's the crucial point that we need to understand from the outset. None of these phenomena actually allow information or matter to travel faster than light in a way that violates causality or the fundamental structure of space-time. Each of these apparent loopholes has very specific limitations that preserve the cosmic speed limit at the most fundamental level. Let's examine each of these phenomena in detail to understand exactly why they don't provide the escape route from Einstein's speed limit that we might hope for. Let's start with quantum entanglement, perhaps the most commonly cited example of apparent faster-than-light effects. Quantum entanglement occurs when two or more particles become correlated in such a way that measuring one particle instantly determines the properties of the other particles, regardless of the distance separating them. When scientists measure the spin of one entangled particle and find it spinning up, they instantly know that its entangled partner will be found spinning down, even if that partner is on the other side of the galaxy. Recent research has actually measured how fast quantum entanglement occurs, and the results are mind-boggling. Scientists have found that the entanglement process itself happens on attosecond timescales. That's quintillionths of a second, making it one of the fastest processes in nature. Some experiments have suggested that if there were a speed associated with entanglement correlations, it would have to be at least 10,000 times faster than the speed of light. This seems to fly in the face of everything we know about the speed limit of light. But here's the crucial distinction that preserves the cosmic speed limit. Quantum entanglement doesn't allow the transmission of information faster than light. When you measure one entangled particle, you do instantly know something about its partner. But you cannot use this knowledge to send a message faster than light. The measurement results are fundamentally random. You can't choose what result you'll get when you measure your particle. You might measure spin up or spin down, but you have no control over which result appears. From the perspective of someone measuring the distant entangled particle, their measurement results also appear completely random. They have no way of knowing, from their measurement alone, that you've measured your particle. The correlation only becomes apparent when both parties compare their results using conventional, slower-than-light communication methods. It's like having two magical coins that always land on opposite sides when flipped simultaneously. The correlation is instant, but you can't use it to send specific messages because you can't control which side your coin will land on. This limitation isn't just a practical inconvenience. It's fundamental to the quantum mechanical nature of entanglement. The very randomness that makes quantum mechanics work also prevents entanglement from being used for faster-than-light communication. The speed of light barrier for information transmission remains completely intact, even in the presence of these mysterious quantum correlations. The quantum entanglement phenomenon reveals something profound about the nature of reality, that the universe can have instantaneous correlations between distant events without violating causality or allowing faster-than-light information transfer. It's a perfect example of how the universe is stranger than we might expect, while still respecting the fundamental speed limit that maintains the logical consistency of spacetime. Now let's turn to another frequently cited potential loophole, the Alcubierre warp drive. This theoretical concept, proposed by physicist Miguel Alcubierre in 1994, seems to offer a genuine way to achieve faster-than-light travel without violating the laws of physics. The Alcubierre drive would work by contracting spacetime in front of a spacecraft and expanding spacetime behind it, creating a warp bubble that carries the spacecraft along at effective speeds faster than light. The brilliant insight behind the Alcubierre drive is that it doesn't actually accelerate the spacecraft to faster than light speeds. Instead, it manipulates spacetime itself to carry the spacecraft along. From the perspective of someone inside the warp bubble, they never exceed the speed of light relative to the local spacetime around them. It's spacetime itself that's moving, carrying the bubble and its contents along for the ride. To understand this better, imagine you're standing on a moving walkway in an airport. You might walk at your normal walking speed on the walkway, but relative to the stationary floor of the airport, you're moving faster than your walking speed because the walkway itself is moving. The Alcubierre drive works on a similar principle, but instead of a moving walkway, it uses expanding and contracting spacetime. This concept is mathematically consistent with Einstein's general relativity. The spacetime geometry proposed by Alcubierre satisfies Einstein's field equations, which govern how matter and energy curve spacetime. In principle, if you could create the right kind of energy distribution, you could generate the spacetime curvature necessary for the warp drive to work. But here's where we encounter the fundamental obstacles that prevent the Alcubierre drive from providing a practical loophole. The energy distribution required to create the necessary spacetime curvature involves what physicists call exotic matter, matter with negative energy density. This isn't just unusual matter. It's matter that has fundamentally different properties from anything we've ever observed in nature. Negative energy density would create gravitational repulsion rather than attraction. It would have properties that seem to violate basic principles of physics, such as the second law of thermodynamics. While some theoretical calculations suggest that certain quantum effects, like the Casimir effect, might produce tiny amounts of negative energy density under very specific conditions, scaling this up to the levels needed for a warp drive would require exotic matter in quantities and with properties that may simply not exist. Moreover, even if exotic matter exists and could be manipulated to create a warp drive, there are additional theoretical problems. Some physicists have argued that quantum effects would likely destabilize the warp bubble, making it impossible to maintain for any practical length of time. Others have suggested that the front of the warp bubble might accumulate high-energy particles that would be released as deadly radiation when the bubble collapses. Recent theoretical work has suggested that it might be possible to construct warp-like spacetime geometries using positive energy density, but these would not allow faster-than-light travel. They would only allow more efficient subliminal travel. So while the Alcubierre drive represents a fascinating exploration of the possibilities within general relativity, it doesn't provide a practical loophole for faster-than-light travel. The third commonly discussed potential loophole involves wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe. Unlike the Alcubierre drive, which manipulates spacetime to move a spacecraft, wormholes would provide shortcuts through spacetime itself. If you could travel through a wormhole, you might be able to reach distant locations faster than light could travel through normal space, without ever locally exceeding the speed of light. The mathematical framework for wormholes comes from solutions to Einstein's field equations. The simplest type, called Einstein-Rosen bridges, arise naturally from the equations that describe black holes. However, these simplest wormholes have fundamental problems that prevent them from being useful for travel. They would collapse too quickly for anything to traverse them, and they would only connect the interiors of black holes, hardly useful for space travel. More exotic wormholes, sometimes called traversable wormholes, could theoretically remain stable and allow travel from one end to the other. But like the Alcubierre drive, these traversable wormholes require exotic matter with negative energy density to keep them open. Without this exotic matter, the gravitational attraction of normal matter would cause the wormhole to pinch off and collapse. Even if we could somehow create and maintain a stable wormhole, there are additional theoretical problems. Some physicists have proposed the chronology protection conjecture, which suggests that the laws of physics conspire to prevent the formation of closed time-like curves, paths through space-time that would allow time travel. Since wormholes could theoretically be arranged to allow time travel, quantum effects might automatically destroy any wormhole that could lead to temporal paradoxes. Furthermore, even if stable, traversable wormholes could exist, creating them would not circumvent the speed of light barrier in the way we might hope. The process of creating a wormhole connection between two distant points would itself be limited by the speed of light. You couldn't create a wormhole to a location 100 light-years away without waiting 100 years for the necessary space-time disturbance to propagate there. Once created, the wormhole could provide rapid transport, but the initial establishment of the connection would still respect the cosmic speed limit. There are other speculative ideas that might seem to provide loopholes. but each has similar fundamental limitations. Some theories propose that space itself might be expanding faster than light in certain regions of the universe, and perhaps we could harness this expansion for propulsion. However, such expansion would be a property of space-time geometry rather than motion through space-time, and it wouldn't provide a mechanism for faster than light travel in the conventional sense. Other ideas involve higher dimensional physics, suggesting that our three-dimensional space might be embedded in a higher dimensional space where different rules apply. While this is an active area of theoretical research, there's no evidence that higher dimensions provide any practical means for circumventing the speed of light limit in our observable three-dimensional world. Some researchers have explored whether certain quantum effects, such as quantum tunneling, might allow information or particles to traverse barriers faster than light. While quantum tunneling does allow particles to cross barriers that would be impossible to cross classically, careful analysis shows that the speed at which information propagates through quantum tunneling processes never exceeds the speed of light. The fundamental pattern that emerges from examining all of these potential loopholes is that the speed of light limit is far more robust and far-reaching than it might initially appear. It's not just a limit on the speed of material objects, it's a limit on the speed of information, the speed of causality, and the speed at which space-time itself can be manipulated. Every apparent exception or loophole, when examined carefully, either doesn't actually allow faster than light information transfer or requires exotic physics that may be fundamentally impossible. This robustness of the light speed limit makes sense when we remember that it's not just a rule imposed on the universe from outside. It emerges from the fundamental structure of space-time itself. The speed of light is really the speed of causality, the maximum rate at which cause and effect can propagate through the fabric of reality. Any true violation of this limit would threaten the logical consistency of physics itself, potentially allowing effects to precede their causes and creating paradoxes that would undermine the rational structure of the universe. The absence of practical loopholes doesn't diminish the fascination and importance of these phenomena. Quantum entanglement has led to revolutionary technologies like quantum computing and quantum cryptography. The theoretical study of warp drives and wormholes has deepened our understanding of general relativity and the nature of space-time. These investigations push the boundaries of our knowledge and reveal new aspects of the universe's strange and wonderful nature. But they also reinforce one of the most important lessons in physics. The universe is both stranger and more constrained than our everyday experience might suggest. The same fundamental principles that make the universe comprehensible and logically consistent also place absolute limits on what's possible. The speed of light isn't just fast, it's the cosmic speed limit that governs how fast reality itself can change from place to place and moment to moment. In exploring these potential loopholes, we discover that the light speed barrier isn't an arbitrary restriction waiting to be overcome by clever engineering. It's a fundamental feature of the universe that emerges from the deepest levels of physical law. While this might seem disappointing for dreams of rapid interstellar travel, it also reveals something profound about the elegant and self-consistent structure of the cosmos we inhabit. The search for loopholes continues to drive cutting-edge research in theoretical physics, and who knows what new insights might emerge from this work. But based on our current understanding, The cosmic speed limit appears to be absolute, inviolable, and essential to the very fabric of reality itself. The universe has given us many gifts, but a way around Einstein's speed limit doesn't appear to be one of them. And there you have it, Cosmic Explorers, the complete journey through one of the universe's most fundamental mysteries. We've traveled from the basic measurement of light speed all the way to the deepest implications of spacetime itself, discovering why nothing with mass can ever break this cosmic speed limit. The speed of light isn't just about light, it's the speed of reality itself, the maximum rate at which cause and effect can ripple through the fabric of spacetime. We've seen how this limit shapes everything, from GPS satellites to the structure of the entire observable universe, creating mind-bending effects like time dilation and the relativity of simultaneity that challenge our deepest intuitions about space and time. Even the most exotic theoretical loopholes, quantum entanglement, warp drives, and wormholes ultimately respect this fundamental barrier, preserving the logical consistency of physics and causality. So here's my question for you. If you could somehow travel at 99.99% the speed of light and experience time dilation firsthand, where in the universe would you go? And what would you want to witness during your journey into the future? Would you explore distant galaxies, witness the birth and death of stars, or perhaps journey to see what humanity becomes millions of years from now? Share your cosmic travel dreams in the comments below. I read every single one and love hearing your thoughts about these mind-bending concepts. If this deep dive into the fundamental nature of reality expanded your understanding of the universe, smash that like button and subscribe to the Lazy Cosmos for more explorations of the cosmos's greatest mysteries. Ring that notification bell so you never miss our journey into the strange and wonderful physics that governs everything around us. Next week, we're diving into something even more mysterious: black holes, where space-time becomes so warped that not even light itself can escape. We'll explore what happens when gravity becomes so strong that it breaks the very fabric of reality, creating regions where the normal laws of physics begin to break down. Trust me, after understanding why nothing can travel faster than light, you'll be perfectly prepared to understand why nothing can escape from a black hole. Until then, keep looking up, keep questioning everything, and remember that the universe is far more beautiful and strange than we ever dared to imagine.